Hi, I am Jasmine Silva, a student of the Master in Science Food Safety in La Universidad de Guadalajara. I'm great to present part of my thesis project. This poster was titled Photocatalytic Degradation under Visible Light of Malachite Green Dye using Dysprosium manganese perovskite. Water contamination has become one of the most pressing issues in recent years. Dyestuffs are the largest group of organic compounds contaminated in water. Dyes have a complex structure that is not biodegradable and makes the dye molecules last longer in the environment. Some photocatalytic materials with semiconductor properties, metal oxides, and metal bases have been used for dye degradation. However, many are only active under ultraviolet light, limiting their use in solar light conditions. Lanthanum-based perovskites have raised interest because of their intriguing properties like thermal and chemical stability, ionic conductivity, magnetic properties, and a narrow band gap that allows for activation by solar light. Dysprosium manganite is a p-type semiconductor material with the perovskite-type structure and a narrow band gap that allows photoactivation by solar light, resulting in a high efficiency in photocatalytic degradation of pollutants. Dysprosium manganite commonly presents an orthorhombic phase, but it could also be found as hexagonal from form under special conditions. A dysprosium manganate was synthesized by precipitation method, employing a dysprosium and manganese nitrates along with formic acid as a precipitation agent. The dry precursor was annealed at 850 Celsius degrees. The materials were characterized by X-ray diffraction, transmission electron microscopy, Fourier transform infrared, and UV spectroscopy. Photocatalytic degradation malachite green dye was successfully induced under artificial light with a wavelength of 405 and an irradiance of 100 milliwatts by centimeter squared. X-ray diffraction patterns of dysprosium manganate powder were compared with hexagonal dysprosium manganate. All diffraction peaks of the sample shows a uniform to gray displacement in contrast to the standard. The precursor image was presented in figure 3A exhibits an irregular morphology when compared with the calcinated powder, which shows a moderate clustering of cubic particles with a mean size of 116 nanometers. The infrared spectrum indicates the absence of organic compounds. Vibration in 675 corresponds to a manganese-oxygen-manganese bending vibration, while 491 and 457 can be attributed to manganese-oxygen vibration. The absorbance spectrum was used to obtain tau plot. The value of n was a half in obtaining the band gap value, that is 2.5 electron volts larger than other reported previously. Finally, a malachite grain solution without material was exposed to violet light with 120 minutes. As a result, 20% of malachite green was degraded in comparison with 31% degradation occurred in first minute when dysprosium manganate was employed. This effect increased to 85% at 30 minutes. Scale ranges demonstrate that the main reactive species contribution to photodegradation of green malachite were hydrogen and hydroxide ion instead of superoxide radicals, which had the least influence.